Okay, we're going to use this slide to apply the first law of thermodynamics to something like a chemical reaction. So here we have a slide showing a reaction, basically burning alcohol, so an alcohol flame. Here's our alcohol. These are molecules of ethanol. And for combustion or burning, you need oxygen, and that's what this is supposed to represent. So these are oxygen molecules. Here's our chemical reaction, our arrow. And when you burn alcohol, it breaks down into carbon dioxide and water. So this is our carbon dioxide. This is our C and OO, which is CO2. Ooh, that's double bond and a double bond. And you get water. Here's our water. All right, so if I was going to write this out like a chemical reaction, it won't be balanced, but it'll be ethanol, which is CH3, CH2OH. There's the CH3, there's the CH2, and there's the OH. That's the molecule of alcohol plus oxygen gives us carbon dioxide and water. Okay, that's the chemical summary of that reaction. But let's look at it from an energy standpoint. So we said before that energy exists in these different forms, and one of the forms that energy can exist in is chemical energy, E-chemical. And we said that E-chemical is energy that's stored in bonds. And there's lots of bonds in this molecule. There's a bond here, and there's a bond here, and there's a bond here, but attaching all these parts of this ethanol molecule together. All these atoms are held together with bonds. All right, so there's lots of bonds in here. And there's lots of bonds, there's a double bond holding this oxygen molecule together. If we were going to add up how much E-chemical was stored in all these bonds, so we'd have to get a measurement of energy for every single one of these sticks. Each one is a certain amount of energy trapped in that bond. Let's just say, to make the math easy, that if you could add it all up, the total number of energy stored in all these bonds is 10 kilocalories. Kilocalories is a unit to measure energy. So if we take the alcohol, sum up all the bonds, how much energy is stored, 10 kilocalories. And when we do the chemical reaction, we end up with carbon dioxide and water. And there's bonds here too, right? There's bonds attaching this C and this O. There's bonds attaching these O's and these H's together. So there's lots of bonds on this side of the equation as well. But if I was to add up all the energy in all these bonds, it's only going to be 3 kilocalories. So this is just a theoretical example. So we started off with 10 kilocalories of E-chemical here on the left side, and we end up with 3 kilocalories of E-chemical stored in the chemical bonds of CO2 and H2O. But if you remember, according to the first law of thermodynamics, we cannot create energy and we can't destroy energy. So it looks here like we went from 10 on the left to 3 on the right. So 7 has disappeared. Have we destroyed 7 kilocalories of energy? No, you can't destroy it. It's got to have gone somewhere. And in this example, what happens is that the E-chemical is released from the bonds in the form of heat and light and maybe sound. I don't know, I've lost my thing. Here we go. So you can see all these like red arrows here pointing. This is supposed to symbolize that heat comes off. When you burn alcohol, you get a flame, and the flame is warm, like from like an alcohol burner. So let's say perhaps 5 kilocalories of heat, E-thermal or E-heat, is released. And we also get some light because the flame glows like a bluish, alcohol burns like a bluish flame. So let's say we had 1 kilocalorie of light was given off. Again, light is E-light, the kind of energy. Ooh, can't see that. Let me try different. There we go. E-light. And sometimes when things burn, they crackle and give off sound. So maybe we also had some crackles and we gave off 1 kilocalorie of E sound. All right, so we started off with 10 kilocalories and it was all stored in all the chemical bonds in these molecules on the left. We ended up with products that had 3 kilocals of E chemical, but we also transformed some of that energy that we started off with into 5 calories of heat and 1 calorie of sound and 1 calorie of light. So we have 3 and 5 is 8 and 9 and 10. So we started off with 10 kilocalories and we end up with 10 kilocalories. We haven't gained any, we haven't lost any. It's just now it's in all these different forms. We have transformed it from purely E chemical on the left to, on the right, some E chemical, some E heat, some E sound, and some E light. We've not broken the first law of thermodynamics. We haven't lost any. We haven't destroyed any energy. We still got 10, the same 10 that we started with. It's just now in different forms. Some of it's heat, some of it's light, some of it's sound. That's how you would relate that idea of the first law of thermodynamics to this reaction. So here's another way to look at it. So here's a graph, and on our y-axis up here, this is measuring the amount of energy, and this is kind of time or the reaction as it goes ahead on going down here. So here's our reactants that we started with, our alcohol and our ethanol and oxygen. And like we said, there are 10 kilocalories total in all these bonds up here, 10 kilocalories. We do the reaction and we end up with products, water and carbon dioxide, and the bonds in there all add up to only 3 kilocalories. So there's less energy in stored in these chemicals than there is in the ethanol. And that's why we have like a downhill slope. We start off with high energy, we end up with low energy. And then the 7 kilocalories that supposedly has gone away to get us from 10 down to 3, that's what's given off or released as light or heat or even sound, and can be harnessed for other things potentially. So this is a chemical reaction shown on a kind of graph, or we call this an energy diagram. And in this chemical reaction, energy is released. And specifically in this example, 7 kilocalories are released. Now this is just a theoretical example. It's not 7 in real life when you burn alcohol, just using some nice round numbers. But because the products have less energy than the reactants are up here and the reactants have more energy, this reaction must cause a release in energy, because you can't go from more energy to less energy without the energy going somewhere. It can't be destroyed, so it has to be transferred to something else or transformed into another form and released. And when energy comes out of a reaction or is released, we call it exergonic. Exergonic. This means energy is released in the reaction. Now in chemistry you might have heard the term exothermic, kind of like a similar idea. So you might have heard exothermic. Now exothermic means heat given out, because thermic is specific for heat, and then exo is like exit, so heat is coming out. Now that's fair enough. This reaction is exothermic because heat does come out of when you burn something, but it's not always heat that comes out. Like in this example, light came out as well, and sound came out because it crackled. And so instead of calling it just straight exothermic, which is only talking about heat, the term exergonic means any old kind of energy. Some kind of energy is coming out, ex meaning exit. So exergonic is somewhat like exothermic, but it just encompasses all the different types of energy that could possibly be released.